Welcome everyone to this explainer. If you are a focused learner looking to really master the inner workings of your data pipelines, well, you're in exactly the right place. Today, we're embarking on kind of an epic adventure, the hero's journey of a Spark SQL query. You know the drill. We write a simple line of SQL, we hit execute, and we just expect magic to happen. But behind that simplicity, it's actually a really complex, perilous journey. And understanding this path is absolutely crucial. It is literally the best way to avoid those dreaded out-of-memory errors and agonizingly slow join times. So let's get right into it. To completely demystify Spark's architecture, we're going to break this down into 4 distinct chapters. First up, the Spark SQL journey itself. Then we'll go inside the Catalyst optimizer. Third, we'll tackle the unified memory model. And finally, we'll wrap up by mastering join strategies. All right, Chapter 1, the planning phase. Imagine our hero here, a simple SQL query, maybe just looking for the average sales per region. When you hit execute, it steps out into this vast, complex world of Spark SQL, totally unaware of the trials it's about to face to get your data back to you. Okay, let's dive into this exact sequence of trials. First off, our query enters the parsers domain, where a tool called antlr checks its grammar and builds an abstract syntax tree. Next, it meets the analyzer. This step checks the Spark catalog just to make sure, the tables and columns actually exist. Then it goes toe-to-toe with the Catalyst optimizer, which actively improves the query. And finally, the physical planner evaluates all the different ways to execute it and picks the absolute most cost-effective path. Moving on to Chapter 2, the Catalyst optimizer. You can really think of Catalyst as our master strategist. Built using functional programming constructs and pattern matching in Scala, it's a super extensible optimizer. Its entire purpose in life is to strip down your query and perfect the execution plan before a single byte of data even thinks about moving. You can really see Catalyst's brilliance when you look at this transformation. Coming right out of the parsing phase, what we have is an unresolved logical plan, basically just a rough, tangled sketch. But once the analyzer checks the catalog and Catalyst does its magic, bam, it transforms into an optimized logical plan. It's sleek, it's verified, and it is completely ready for action. Now, to get that plan so sleek, Catalyst applies some pretty ruthless rule-based optimizations. It uses predicate pushdown to filter data as early as possible right at the source. Then it uses projection pruning to grab only the columns you actually need, which drastically cuts down on data transfer. And it uses constant folding to simplify any constant mathematical expressions before the query even runs. It's all about doing the heavy lifting up front. But wait, Catalyst has one more massive trick up its sleeve: whole stage code generation. Catalyst programmatically builds abstract syntax trees and literally compiles them into Java bytecode at runtime. This generated code performs almost exactly like handwritten, hyper-tuned code, totally blowing standard interpreted execution out of the water. It strips out the overhead of virtual function calls and massively speeds up your CPU-bound in-memory processing. It is a total game changer. Which brings us to Chapter 3, the unified memory model. Here, we shift our narrative over to the executor JVM. And let me tell you, this is a highly contested battleground. This is exactly where our optimized query has to violently fight for the resources it needs to survive. Prior to Spark 1.6, memory had these really static and flexible boundaries. But the unified memory model completely flipped the script by splitting the heap into dynamic regions. First, you've got reserve memory. That's a hard-coded 300 megabytes strictly set aside for Spark's internal engines. And no, you cannot change this. Then there's user memory for your own custom data structures. And finally, the rest is unified memory, which dynamically shares space between storage, like your cached data frames, and execution, which is doing all the heavy lifting for things like shuffles and joins. So here is the absolutely crucial takeaway. 60%. Only 60% of your usable heap after you pay that 300 megabyte reserve tax is actually unified managed memory that Spark can use for its core storage and execution tasks. The other 40%, that just belongs to user memory. Let's put that into perspective and see why this matters practically. Developers often just assume, hey, I provisioned a 16 gigabyte executor, I have 16 gigs of workspace, right? Nope. If you take 16 gigs, subtract that 300 megabyte reserved memory, and then take 60% of what's left, you only end up with 9.65 gigabytes of unified managed memory. That is vastly less workspace than most people realize. And honestly, it's exactly why tasks run out of memory so often.
Inside that limited unified memory pool, there's a very ruthless eviction rule. Execution memory and storage memory share the exact same pool, but execution always gets priority. If your query needs memory to pull off a join or a shuffle, it will actively evict and overwrite your cached storage data to get it. Why? Well, Spark's designers knew something fundamental. A computation failure that crashes an entire job is vastly more expensive than just dealing with a simple cache miss later on.
All right, final stretch. Chapter 4, Mastering Join Strategies. So our query has its plan, it knows the memory battleground, and now it has to combine massive data sets. Pulling this off efficiently requires some highly tactical decisions on how to execute the join. Looking at the 3 main join strategies gives us a really complete picture of these tactics. The sort-merge join is your default for massive data sets. It's robust, for sure, but it requires heavy network shuffling and a lot of CPU overhead just to sort everything. Then there's the shuffle hash join, which avoids the sorting part but still requires those heavy network shuffles. But right at the top of the podium, we have the broadcast hash join, which requires absolutely zero shuffling on the smaller data set.
Let's focus on the broadcast hash join for a second, because it is by far the most efficient strategy. Instead of moving massive chunks of data all across the network just to match keys, Spark takes the entire smaller table and literally copies it, or broadcasts it, to the local memory of every single worker node. It builds an in-memory hash mapper right there, which means the join happens entirely locally. No sorting, no heavy network shuffles. It's brilliant.
Now, by default, in open source Spark, a table will automatically be broadcast if it's under 10 megabytes. However, if you're running on platforms like Databricks with adaptive query execution turned on, this threshold gets dynamically evaluated and is actually often pushed to 30 megabytes or even higher. And remember, you can always force this behavior using a broadcast hint right in your SQL code to make absolutely sure your query skips that expensive shuffle phase entirely. So, we followed our hero query all the way from a raw string of text right through the Catalyst Optimizer's rule-based gauntlet into the strict borders of the unified memory model and finally through the highly tactical choice of a broadcast join. The question is, the next time you see an out-of-memory error or you're staring at a painfully slow query, are you just going to blindly throw double the hardware at it? Or will you use your new understanding of this journey to check your execution plan, verify those memory partitions, and write truly optimized code? Think about it. Thank you so much for joining me on this explainer. Keep learning, and I'll see you in the next one.